Hello everyone, today I'm going to present inference of jump using the wavelet variance. This is a joint work with Moto Chitani from the University of Tokyo. So the objective of the paper is to apply statistical inference of jumps in non-parametric regression model with long memory noise. We propose a new test statistic for the percent of jump. If later we detect a jump, then we're going to propose a new sequential application of the test to estimate the number of jump and later locations. So here's the roadmap, model, motivation, test statistic based on the wavelet variance, how to test for the hypothesis of non-jumps, then estimating number of jump and the location. For the simulation and empirical application, please see the paper. So the model one is yi equal to fin plus epsilon I. So the fi here is non-parametric regression. So under the h0, fx is equal to fcx, which fc is continuous differentiable equation or trend. However, under h1, fx have two parts, the continuous differentiable part, fcx, and fjx, which is the jump part, which can be written in terms of representative form of the sum of the step function. M0 is number of jumps, lambda L is jump location, and DL is jump size. So for the noise part followed and can be characterized by the so-called Hertz parameter. When h equals 0.5, epsilon is an independent Gaussian error. When h equals from 0.15 to 0 to 1, epsilon has a long-run dependence or long memory. So given the model is very general to allow for non-parametric regression model with long memory noise, the existing approach from 1995, 1999, usually based on the supreme type of text statistic. However, we know under H0, one supreme type statistics convert very slowly to extreme value distribution. So our solution is to based on a robust estimator of the variance of wavelet coefficient, which is convert faster to normal distribution. So the advantage of that is in our approach, in thin sample, we have a better size control to test H0, and also better size precision and better precision of estimating H0, basically the number of jumps. So let's look at how we propose the wavelet variance estimation. So here we propose the discrete wavelet transformation. Basically, per se, here is the wavelet function. AI is a component which can be compute the discrete wavelet transformation. A here can be the Y, can be F, and can be noise. And the per se, which the wavelet function is integrated to 0 compared to the kernel integrated to 1. So if we apply this wavelet transformation on both sides of the model, we have Wy, Jk, which is denoted at the scale J and location K. And then we have right-hand side, we have Wf with the wavelet transformation of the trend, and Wbk, the wavelet transformation of noise. So the property of Wf is spatial adaptable to the pointwise smoothness of Fx, and the Wb is decorrelate the long memory noise, epsilon I. So recall this transformation on both sides, and H0 for all the location K of the wavelet transformation, Wyjk is probably equal to Wbh, because the wavelet transformation of Wf is probably compared and negligible compared to Wbh. And H1 for the location K near jump, Wy is proximally and dominated by the Wf, which coming from the trend function. More particularly, is dominated from the jump part, which is Wfj, the jump transformation. And otherwise, for the location far away from jump, Wy is approximated by the Wbh. Then you can think about near the jump, the wavelet transformation of Y can be dominate the component from jumps. So remark here, the 1995 and 1999 propose a text statistic based on the supremum of Wy here. So our wavelet text statistics is based on the wavelet variance. So here the sigma j square is how we define the wavelet variance. Here in the literature, there's two versions. One is a robust version, which is the W robust to the jump in the trend. So which is, as you say in the last line, is the median absolute deviation part. And of course, we have a non-robust version, which is the sigma jk square, which is the sample average to estimate the wavelet variance based on the wavelet coefficient. So the intuition, since the sigma j theta is robust, while the sigma j hat is not robust, so we're going to take their difference as our text statistic. And it's 0, both are consistent, so the difference are smaller. However, under the now, since the height part is not robust, it will be larger, and the sigma theta is still consistent. So the difference and the another alternative will be large. And this gives out the power of our test statistic. In the paper, we derive its size and also the power at H1 and H0. Similar, we also going to propose this GJK to estimate the per second procedure of the number of jump and the location. So basically the intuition is, if we in the step 1, we allow M0 equal to 0, basically no jump, and H1 is M0 bigger than 0. So if DJK is bigger than the critical value, then we're going to move to the step 2, which we update H0 to the M0 equal to 1, and H1 to the M0 bigger than 1. If still reject, we're going to move step 3 until we cannot reject this test statistic based on this critical value, C lambda. Of course, you need to update this the test statistic as well, because once you estimate the potential jump location, you're going to remove that from the computation of DJK. So in the paper, we show the number of jumps and the location can also be estimated consistently. So then this slide just provide the how we're going to convert this infeasible test statistic, which is the denominator, to a feasible version. So I'm going to stop here and see you in the poster session.